So we're going to continue our series of lectures on training neural networks. Do we have any questions from the past couple of weeks? Any questions? None? OK. So again, your name tags, if you please. Here's where we were. When we last checked, we found that training neural networks through empirical risk minimization was set up as follows. We were given a collection of training instances comprising input-output pairs. And so we had each training instance had an input X and a desired output, the output that you want the network to compute. And we defined a divergence between the actual output of the network and the desired output. Do you mind shutting your laptop, please? Please do not open it. If you want to open your laptop, go outside, finish your work, and come back, right? So we defined a divergence between the desired output of the network and the actual output of the network. The loss was defined as the average of this divergence over the entire training set. And this loss, once the training set is specified, the loss is just a function of the network parameters W. And so this is what we would minimize the loss with respect to W, where the network parameters comprise the set of weights for all of the perceptrons in the network and their biases. Now, before we continue, I'm going to introduce some notation. We're going to be representing weights as W, biases as B. And we're going to assume that the network is layered. We've described layers before, and I've also explained what I mean by a layered network. So the input is going to be X, but often we will also just represent it as Yi superscript 0, which is to say the 0th output. This is for notational convenience. Then the weights to the ith layer are represented by a superscript I. So the weights to all the neurons in the first layer have a superscript 1. The biases have a superscript 1 as well. The bias to the jth neuron in the first layer is B subscript J superscript 1. So the subscript, in the case of the bias, indicates the index of the neuron. And in the case of weights, there are two subscripts, I and J. I is the source neuron, J is the target neuron. So it's the weight from the ith neuron of the previous layer to the jth neuron of the current layer. Now, so when we want to perform gradient descent, when we want to minimize the loss, we're going to do so using gradient descent. This is how we saw we'd do it. We would initialize all of our parameters, and then we'd iteratively take a step in which direction? Opposite the gradient of the loss with respect to the parameters. So at each step, the weights are going to be updated against the gradient. And again, is the gradient the derivative of the loss? It's a transpose of the derivative, the way we defined it. And so we're going to keep doing this until the loss no longer changes. Why do we have the check on the loss and not on the derivative? Anybody? Do you remember? Yes?
The loss can be minimized even where it's not the derivative is not 0.
The loss can be minimized even when the derivative is not 0. We saw this at the boundaries of the feasible set. The derivatives may not be 0. So now if I want to expand this out, here's what it's going to be. There's your loss again. It's the average of the divergences over the training set. And we'd initialize all the parameters, which are the weights and biases. I'm going to assume that the bias is also represented as a weight, which means that I have introduced an additional component to the inputs whose value is fixed to 1. And we know that the gradient is simply a vector of partial derivatives. So which means that all that gradient descent does is to adjust each parameter in the direction where the adjustment is guaranteed, or at least locally, to decrease the loss. So for each parameter Wij, we take a step against the derivative of the loss with respect to that parameter. So this loss, the derivative of the loss with respect to network parameters Wij, is what we need to compute. Now, how do we compute that? That's what this lecture and the next lecture are all about. So once again, the loss is the average divergence over the training set. So if I take the derivative of the loss with respect to any parameter. Then due to the linearity of the summation, this means that this is just the average of the derivative of the divergences for individual training instances with respect to the parameter. And so what we really want to compute is this term here, which is the derivative of the divergence with respect to individual network parameters, Wij. So we will see how we do this. Any questions? Any questions on Zoom? No, okay. So we're going to take a slight detour at this point and begin looking at, wait a minute. We're going to take a look at some simple rules of differentiation, if I can find myself a chalk. Yes, chalk. Now, consider any function y equals f of x. So, do you remember how we define the derivative? Anybody?
Perturbation of x.
So, anyone?
Transpose of the scalar.
The transpose, but at a finer level, what was the derivative? So if I had, it's there on the board, if I said y equals f of x, then the derivative was the term that multiplied a small perturbation in x to give you the corresponding perturbation in y. This is something that must be burned into your mind because that's how we define the derivative. You know, dy over dx is improper notation for everything except, you know, scalar functions or scalar variables. So now this I can represent in a specific manner. I can say that the variable x influences the variable y. And I'm going to introduce something called influence diagrams over here. Now this edge over here also gives me information on how much perturbations of x will perturb y. And so these could be partial or full derivatives. But then this is how this notation indicates that perturbing x perturbs y. And so specifically, this means that if every delta x is going to result in a delta y, we're just using the little graph theory, graph-based notation we have over here. The value of delta y is going to be the input to this edge multiplied by the weight of the edge. So this notation, any confusion about this notation? No. So this is simple. For any differentiable function y equals f of x with derivative dy over dx, we know that delta y must be equal to, for small enough perturbations of x, this must be equal to the derivative times delta x. And so the influence diagram, x influences y. This edge between x and y carries the weight which is equal to the derivative of y with respect to x. And so just using the simple graph-based notation, any perturbation delta x going into this edge multiplies the edge weight to give you the corresponding perturbation in y. Now, here's a different function. Y is a function of many variables, x1 through xm. In this case, using the same notation, what would the influence diagram be like? Anybody? Yeah.
Many edges.
Exactly. So I'm going to have x1, x2, xn, all of them are going to influence y. Using the same notation, Miguel, what would the weights of these edges be?
The partial derivatives.
The partial derivatives of y with respect to x, the corresponding x. And now using the same, the rules for graphs over here, what would delta y be from this picture? So again, going back, this also means that if I have a delta y here, all of these have delta x's, right? What would delta y be?
Summation of the sources.
This is going to be the total incoming, the total incoming information. That's going to be, summation I dy over dxi delta xi. Everybody comfortable with this representation? We're going to see it a few more times in the next few classes. And so here's the influence diagram. the derivative diagram is going to look like so, which gives you this distributed derivative rule, which all of us were familiar with from school. Questions? No. Okay. So now let's look at a function of this kind, where y equals f of g of x. So here again, the influence x influences the function g, which I'm also representing. I could have introduced a variable, but I'm just going to call it g for now. And this influences, x influences g, g influences y, right? This making sense to everybody? What would the edge weights be? Anyone? In this case, what would the edge weights be? This is going to be dy over dg. These are partial derivatives, but I'm just going to write full derivatives. And this would be dg over dx. Okay, so given this now, what is dy in terms of, or what is delta y in terms of delta g? It's going to be dy over dg times delta g, correct?
Yeah.
What is g in terms of x? dg over dx times delta x. So plugging this over here, I'm going to get dy over dx, dg times dg over dx delta x, correct? So if I were to combine all of these, what is the edge weight over here? Anybody? What is that?
dy by dt.
That's going to be this term over here, correct? So this is dy over dg times dg over dx. And this is the derivative of y with respect to x. This is the, what rule is this? This is the famous chain rule. If you just draw the pictures out, it makes sense, right? And now, so that's what we've got. Now suppose I have something of this kind. Y is a function of many functions, each of which is a function of x. Then what would this diagram look like? Anyone? Is there an eraser here? What would this diagram look like? Like a perceptron. There's got to be an eraser here. Explain. So this is going to look like so, right? I have g1 through gn all being functions of x. So I would have x influencing g1, g2, gn, and each of these in turn is going to influence y, right? Everybody with me? What weights would these edges carry?
Partial derivative.
This is going to be, what is this one? dy over dg1. This is dy over dg2, dy over dgn. And what about these guys?
dt1 over dx.
dg1 over dx, dg2 over dx, and so on. So now if I were to write delta y out, what is delta y? Anyone? Can you say that again loud, please?
Summation of the product of these.
This is going to be, first, this is going to be dy over dgi delta gi. But then we know that delta gi is simply dgi over dx times delta x, right? So this is dgi over dx delta x. And so if I write the relationship between y and x down, this is what we get. So this is our, what is the derivative rule over here? If I were to write it down, that's simply going to be the summation, the derivative of y with respect to x is the sum over all g's of the product of the derivative of y with respect to g and the derivative of g with respect to x. You can derive this using math, but once you actually draw the pictures, it becomes quite obvious, right? Questions? Any questions? No. Okay. And so for any nested function for L equals f of y, where y is g of z, we know that dl of dz over dz is dl over dy times dy over dz. And for any function f equals any function of many variables where all the variables are a common function of x, or functions of x, of a common variable x, then the derivative of L with respect to x is simply the distributed chain rule, where you sum the products of partial derivatives over all of the contributing functions g, right? Okay, questions? None. So now that's just a little background. Our problem is, how do we compute the derivative of the divergence with respect to individual network parameters? Again, this derivative tells us how much perturbing the parameter is going to perturb the divergence. If increasing the parameter reduces the divergence, you want to increase it. On the other hand, if decreasing the parameter reduces the divergence, you want to decrease it, right? So first there's a pull. Okay, guys, time's up. Someone on Zoom, can you answer the first question? Zoom? The first question, pardon me? Okay, over here, the lady at the corner with the laptop open, can you answer the second question? Pardon me? Second one, right? Second one is true? You really should keep that laptop shut and pay attention. So the first one, the chain rule of derivatives can be derived from the basic definition of derivatives. And the influence diagram graphically shows all paths and variables through which one variable influences another, right? That's all we have covered so far. So now let's go back and look at how we can compute derivatives. I'm going to use this little illustration over here, which is a very simple network of just two inputs. It has two hidden layers. And let me expand on each of the perceptrons in the network. Each of the perceptron has two stages of computation. First, you compute an affine variable, and then the affine variable is put through an activation function, right? And so if I were to annotate all of the parameters of the network, these are all the weights. And here I'm not explicitly introducing a bias. I've just added an extra component 1 at every layer. So the weight of that extra component showed by the little red box should give you the bias. This is just for notational convenience. So in every case, this term here, which starts from the 0th, which has the 0th index in the first location, represents the bias. And let me also annotate the remaining variables. So the z's represent the affine variables that get computed from the output of the previous layer. So z2 superscript 1 represents the affine value at the second neuron of the first layer. So in general, z subscript I superscript j is the affine value at the ith neuron of the jth layer. And so also y represents what we get when you apply the activation function to the affine value. So y subscript I superscript j represents the output of the ith neuron in the jth layer. So we are annotating every single variable of every single neuron explicitly in this manner. And now the output of the neuron of the network can be compared to a desired output. You get a divergence. And our question is, how does perturbing any weight, say this one, influence the final divergence? This is what we must compute. But the way we will do it is that we will work our way backwards. So the first thing we will do is to determine how much perturbing y will perturb the divergence. But then we will combine that with how much perturbing z perturbs y, and then chaining the two, you can figure out how much perturbing z perturbs the divergence. And then you can take a step back and so on. So in order to compute all of these derivatives, you need to know each of the intermediate variables. Again, we know from the last class and from the various pictures I've drawn that the value of the derivative depends on where you compute it, which means that we need to know all the intermediate and final output variables, all the z's and y's of the network, for us to be able to compute the derivative. So the first thing we will do is to compute all of these intermediate values, because we will need them to compute the derivative. This is what's called the forward pass. And let's see how that's done. If you're training the network, you would have initialized all the parameters of the network. If you're in the process of training the network, you may have updated these parameters, but at any given time, all of the network parameters will have some value. Chenjia, do you want to go wash your face or something? Okay. So again, we're going to use the same. I'm explicitly introducing the bias again. I'm going to be, the 0th term is the bias. So I'm just introducing this 1, and the bias is its weight. And the input is going to be represented as the 0th layer. So it's just yi superscript 0, just for notational convenience. And then once I do this, the affine value at this neuron is simply going to be the first input times this weight plus this input times this weight, and so on. You'd be summing over all of the inputs to the neuron, and you'd be taking a weighted sum. So z1 superscript I is going to be the summation over all inputs of all inputs I of wi1 times the input yi. The superscripts just take care of the layers. So there's nothing particularly complicated about this equation, so I don't have to go into this in detail, do I? Easy enough. So we can repeat this computation for every single neuron in the layer, and thereby you would have obtained the affine values for every neuron in the first layer. Subsequently, you can just apply the activation functions for all of these neurons, and you're going to get the outputs of the neuron for the first layer. So very easy. The computation is very simple indeed. And then I can keep repeating this process. Now I can compute the affine values for the neurons in the second layer using the y values output by the first layer. And then I can pass those through an activation and keep doing that until eventually I get the output of the final layer of the network, which is the output of the network. So if I were to write this down as pseudocode, this is what it's going to look like. I'm going to go through the layers. K represents the layers. yi0, the 0th layer values are just the inputs. And then for each subsequent layer, I compute I loop through all the neurons. For each neuron, I compute the affine value as the weighted sum of the outputs of the previous layer. And then I apply an activation to this affine value to get the output of the neuron. When I'm done computing this, I'm going to have both the affine value and the output of every neuron of every layer. Questions? Yeah.
Should we just think of the bias? I mean, the notation doesn't have like a 9 plus 1, so it's basically like the bias term is.
The bias term is the 0th term over here.
Yeah.
The little red box.
But in the notation, like summing over I, like we just assume that, from there isn't like an additional term that we include in summations for the bias term, we just kind of folded it.
So the bias term is just folded in. If I go starts from 0, I have the bias term folded in. This is just notational convenience. That's it, right? I keep switching back and forth because it depends on how much space on my I have on my slides, really. So you must forgive me for this. I can write the pseudocode for this. Very easy again. I have set yj0 equals xj for all of the input dimensions. We loop through the layers. Within each layer, we loop through all the neurons. For each neuron, you compute the affine value and then pass the affine value through an activation to get the output of the neuron. And the output of the final layer is just the output of the network. Trivial. And so we have now computed all of these z and y values. We must now use these to compute derivatives going backwards. Now the way we will compute derivatives is as follows. We'll start off by first computing the divergence between the actual output of the network and the desired output. Then we take a step back and determine how much perturbing the output of the network will perturb the divergence. So that's going to give us the derivative of the divergence with respect to the output of the network. And then we take a step back from there and we compute how much perturbing the Zn will perturb y. We have already computed how much perturbing y will perturb the divergence. So chaining the two, we get an idea of how much perturbing the z's will perturb the divergence. And we can keep doing this going backwards. We'll go back and compute the derivative with respect to these weights. Again, we can use the same principle. And then compute the derivative of the divergence with respect to these y's and these z's and these weights all the way back to the beginning. So since we are starting the derivative, and this is how we must do it. You cannot compute the derivatives going forward because we need to know how much these perturbations are going to influence the final output. So you have to start at the end. And so since we are computing derivatives going backwards from the output to the input, this is called back propagation. Now let's actually go through the math. So first, we assume we have the divergence. Then the divergence function is something that we design. And for each divergence, if you were paying attention in the last class or if you saw my Piazza post, you know how to compute the derivative of the divergence with respect to the output of the network. That's just the derivative of the I'm just assuming that this is given because every divergence has its own derivative. And subsequently, we're going to apply the chain rules that we just saw. The one that we will apply most is this one, that if we have L equals f of y, loss is the function of y, where y is a function of z. So the loss is the function of the output of a network of the neurons, and the output of the neuron is a function of the affine value z. So in that case, the simple chain rule tells us that the derivative of the loss with respect to z is the derivative of the loss with respect to y times the derivative of y with respect to z. So let's apply this over here, right? We're going to compute the derivative of the divergence with respect to these y and the z, but then applying the chain rule, that's just for each z, that's the derivative of the divergence with respect to y times the derivative of y with respect to z. That's just the chain rule. I've written it backwards for reasons you'll see, okay? And this derivative of the divergence with respect to y was already computed because we assume we know this. So the only thing that remains to be computed is this guy. What is the derivative of y with respect to z? But this is easy. This is just the derivative of the activation function computed at this z. And this z was computed during the forward pass. And so I can plug that value right here. And now, trivially enough, I have the derivative of the divergence with respect to the affine values at the output layer. Any questions? Yeah.
What was computed on the forward pass?
We computed the z values, right? We know the z.
Okay, yeah.
This was computed. And so we need the derivative is going to be dependent on the location where you computed. And so this was computed, right? Now, the next thing we want to do is to go back and compute the derivatives with respect to these weights. Now, using the chain rule again, the derivative with respect to any weight wij for the nth layer is simply going to be the derivative. Again, the weight wij influences the z, right? So this is going to be the derivative of the divergence with respect to z times the derivative of z with respect to the weight. That clear to everybody? And this first term was just computed. So the only thing that remains is this one. What is the derivative of z with respect to wij? Now z is an affine value, and we know that, in this case I'm calling that zi, zj, right? So if there are a bunch of inputs, and if I'm looking at zj, and if I want this derivative from this wi, which comes wij, which comes from input I, so zj is going to be wij times xi, which is this term, plus a whole bunch of other guys which don't depend on wij, plus something else. Plus I'll just call this some f, okay? S for something else, okay? Now what is the derivative of zj with respect to wij in this case? Can you say that aloud, please? This is I, right? This is just xi. So the derivative of zj with respect to wij is just xi. This which just happens to be the output of the ith neuron in the previous layer, which is yi superscript n minus 1 in our case, which was computed in the forward pass already. And so I can just plug this value here. So the derivative of the divergence with respect to wij is yi from the previous layer times the derivative of the divergence with respect to zj. So in general, if I have a connection of this kind, I have yi n minus 1, wij, this is zj. Now eventually zj is going to influence the divergence. So I can say that the derivative of the divergence with respect to wij is going to be the derivative of the divergence with respect to this guy, zj, times the input to the connection, yi. And so also the derivative of the divergence with respect to yi is simply going to be, what's that going to be in this case? I don't think it's very clear what I've written. Let me draw this more carefully. So if I have yi n minus 1, and this has a weight wij, from this I compute zjn, and zj eventually is used to compute the divergence. Then the derivative of the divergence with respect to wij is simply going to be the derivative of the divergence with respect to zj and times what? That's simply going to be wij, correct? What about the derivative of the divergence with respect to yi in this case? Sorry, this is going to be yi, right? Correct. What is the derivative of the divergence with respect to yi? Used by symmetry, that's going to be because these two are getting multiplied, right? So again, the second one is not so simple, but here's this first term. We've already seen this. What is the derivative of the divergence with respect to wij? It's the derivative for zi times zj times yi. But then when you look at the derivative of the divergence with respect to this term here, wait a minute, any of the yi's, it gets more complicated. Now we have to consider this distributed chain rule. So if I have a function, if I have any variable x which influences a whole bunch of functions, all of which influence the final loss, then you've got to sum the derivative over all of the outgoing arcs. So in our case, if you look at this one here, this yi influences all of these z's. All of those are in turn used to compute the final divergence. And so if I want to compute the derivative of the divergence with respect to this yi, I have to sum over all the z's. And what I'm summing is the derivative of the divergence with respect to z times the derivative of z with respect to yi, right? So it's not as simple as what I just wrote. And what is the derivative of z with respect to yi? Right, this term's already computed. And because the derivative z is simply wij times yi times other terms. So the derivative of zj with respect to yi is simply wij, which I can plug in over there. And that's going to give you my derivative rule for computing the derivative of the divergence with respect to yi. This makes sense to everybody? I know I got a bit tangled, but there's nothing particularly complicated about this. Questions? Right? No. Okay. And so I can use the same rule to compute the derivatives for all of the yi's in the penultimate layer. And once I have done that, I can use those to take a step back and compute the derivatives for the z's, the affine terms, simply by multiplying the derivative for yi by the derivative of the activation functions. And then once I have those, I can take a step back, compute the derivatives for the weights. And the derivative, again, for any weight wij for the n-1th layer is the derivative of the divergence with respect to zj for the n-1th layer times the yi for the n-2th layer. And so I have the derivatives for the weights. Then I can take a step back and use the same rule as before and compute the derivatives for the y's and so on. Now, there's something interesting, and I can do this going all the way backwards. Now, and I can even compute the derivative eventually with respect to the input of the network. Sometimes you want to see how much perturbing the input changes the loss. And there are situations where that's required and we can compute it. So if I write the whole thing down, here's what the pseudocode would look like. First, you assume that you have the derivative of the divergence with respect to the outputs of the network. Then multiplying that by the derivative of the activation function for the output layer, you get the derivatives with respect to the affine values at the output of the network. Subsequently, here's the interesting thing. I keep going back. At each time, I compute the derivative with respect to the y's, then take a step back, compute the derivative with respect to the j's, and then also compute the derivatives with respect to the weights. And here's what you get. The derivatives of the divergence with respect to the y's is simply a weighted sum of the derivatives of the divergence with respect to the subsequent z's. So when I'm taking a step back, computing a derivative with respect to the y's is simply a weighted sum of the derivatives of the next layer. Computing a derivative with respect to the z's simply multiplies by the product of by the derivative of the activation function. The one-off is the derivative with respect to the weights, which is going to be the derivative for z times y, right? So if I write the pseudocode, this is what it looks like. For the output layer, I can compute the derivative with respect to of the divergence with respect to the y's, and then finally with the affine terms. And these red terms in red are where we are computing derivatives for the parameters. We just saw how to do this. But the rest of it looks a whole lot like what you would do in the forward pass. In the forward pass, what did we do? We computed affine terms as the weighted sums of the outputs of the previous layer. And then we applied an activation function to it. In the back, so that this is what the forward pass looked like. At each point, we computed a weighted sum of the outputs of the previous layer and then applied an activation to it. That's exactly what we are doing here, except we are doing this going backwards, using exactly the same weights. We are computing a weighted sum of the derivatives at the next level of the network. And then we are taking a step back, and instead of directly applying an activation function to it, we're just multiplying by the derivative of the activation function. Because these are derivatives, now it's f prime rather than f. But it's essentially the same as the forward pass with the network flipped, the network flipped, and the activation functions are replaced by their derivatives. And just the one-off computation is the derivatives for the weights themselves. Any questions? So, yeah. So you used your 30 seconds. We'll give you another 15. I think most of you are done. So people on Zoom, can you answer this question? Is the first statement true?
False.
No.
Okay, what about the second one? Is it
No.
true?
False.
What about the third one?
True.
Yes.
So back propagation is this process where we propagated derivatives backwards. It's the mechanism that we use to compute derivatives. Back propagation is not the training algorithm. Back propagation is merely the procedure that we use to compute derivatives. Those derivatives are plugged into other rules, like the gradient descent rule, to actually update the parameters. Everybody clear about that? Yes.
So during the forward propagation, we use weight. So like we use activation function on weights. But essentially in back propagation, we compute its derivative. So that change can be anywhere on the curve. If we are taking curve, like initially that change can be for any weight because it's a change. Like
I'm not sure I understood the question. Can you clarify?
so, if let's say we have a curve, we have derivative is basically a slope. Slope can be same at some particular places. So for a particular weight, we can have that same derivative at multiple places, right?
So if you think of it this way, so let me draw my loss function as a function of the weight. So this is my weight, any weight, and this is my loss. My loss is going to be some funny curve. So at one point, we really need to know where we are. This is not just a function of W, it's also a function of other things like Z's. Just looking at the weight is not sufficient as to tell you what the Z values are. The input is, the space is multidimensional, right? And so the first thing we're going to do is to use this weight to also determine the Z. And that's going to give you the precise location. Only then can you actually check the slope. So that's what the forward pass is doing. Did that answer your question? Okay. So we made some assumptions so far. That the output of one neuron directly affect the computation of other neurons in the same or previous layers. That inputs to neuron only combine through weighted addition, and that activations are actually differentiable. So all of these conditions are often not applicable. We won't discuss all of these in class, but these exceptions in class, but they are on the slides. We will look at a few exceptions. The first is vector activations, which we have already encountered. Now, we have seen that in the way we've defined the network, modifying one affine value only modifies the corresponding output. But in the case of vector activations, we can have an activation where modifying one affine value changes all of the outputs. We looked at one particular example in the last class. Which was it? Softmax, right? And so here's what would happen. In the case of the scalar activations, y equals f of z, dy over dx is dz is just f prime. Over here, you have a vector of y's and a vector of z's. And so the way to think about it, so in the scalar activation, each z influences one y. Here, each z can influence all the y's, and each y is influenced by all the z's. So here, in the case of the scalar activation, when I'm going backwards and computing derivatives, if I want to compute the derivative with respect to any particular z, I just have to go past this one line. It's the derivative of the divergence with respect to y times the derivative of y with respect to z. But if I have a vector activation, things are slightly different. Because each z influences every one of the y's. And all of these y's eventually influence the divergence. And so if I want to compute the derivative of the divergence with respect to any particular z, I'm going to have to sum over all of these terms. And so the derivative of the divergence with respect to z over there is going to be the sum over all of these outputs of the derivative of the divergence with respect to the yi times the derivative of yi with respect to z. So it becomes a bit more complicated. Now, let's take a look specifically for the case of the softmax. In the case of the softmax, we know here's the equation for the softmax, we know it. For any particular yi, it's going to be the exponent of the corresponding zi. You exponentiate the zi, and then you normalize the whole thing to sum to 1, right? Now, as you can see, every single z influences each y. Now, and each z influences every y. So now if I want to compute the derivative of the divergence with respect to any given z, I have to compute all of these derivatives. The derivative of each one of these y's with respect to z. Now, it's easy enough for us to derive these derivative rules, but I'm going to ask you a question that we've already got the answer to in the last class. What do you think the sign of the derivative of yi is going to be with respect to z, of the corresponding z? If it's just a straight line, if it's this one, just this one, what is the sign of the derivative? Positive. What about this one?
Negative.
Negative, right? Because increasing any z increases the corresponding y, and increasing any z decreases the corresponding y. And so indeed, that's what the derivatives look like. So the derivative for any, now there's another thing, right? If yi is close to 1, there isn't a lot of space for it to move any further. So increasing z is not really going to change yi a whole lot. Similarly, if yi is, so if y is very close to 0, if it's way out, it's very small. Small changes in y is not going to change z very much. And so the derivative has this property for the pass-through. It's positive, and it's going to be y times 1 minus y, which captures the fact that this equation actually looks like this. For any given input, for any given specific output, yi, if I have fixing all the others, if I fix all the other z's and change just that one z, that's going to look like a sigmoid. And so way out to the left, when yi is really small, the derivative is really small. When yi is 0, when yi is 1, the derivative is 0 also. It's only in between where yi is distant from both 0 and 1 that it has a significant value. And so you can see that from the equation. It's yi times 1 minus yi. It's positive and has this property that it basically goes to 0 when at both extreme values of y and takes meaningful values only in between. Now, if you look at the cross derivative, that looks like minus yi times yj. You can intuit it similarly, but the first most important thing to do is to see is that it is negative, right? And the larger it is, the more negative it is, because the faster you want it changes. So, questions? And so this is what you would plug in to the formula if you were computing the derivative of the divergence with respect to any given yi. Now, this was the softmax. There are other cases of vector activations that are on the slides. Please look them up. They will appear in the quiz, okay? There's another kind of activation which is of interest to us, which is the ReLU activation. This is not differentiable at a specific point. Where is it not differentiable?
0.
At 0, because it's got a corner. So in this case, if you go through the theory, they're going to tell you to look at something called subderivatives and subgradients. So what exactly are subgradients and subderivatives? For convex functions, if I have a function of this kind, a corner, then when you look at a continuous function, it's just the slope of the tangent. But there's no unique tangent out here. On the other hand, I can draw a whole lot of lines, all of which basically just touch the function at this corner without actually crossing it. The slopes of all of these lines are called subgradients. And so you can use any one of those values in your gradient update rule. But there's a slightly different way of looking at it. So here is your ReLU again. You can think of the ReLU as a function which rotates from 0, slope 0 to slope 1 instantaneously. If I think of it this way, now how do we define a derivative? A derivative says how much y will change for a small perturbation in x. Suppose you're arriving at this ReLU from the left. Will a small perturbation in the input z change y? So what will the slope be? If you're arriving from the right, will a small increase of z increase y? And what's the slope? And so you've gone suddenly from slope 0 to slope 1, but you can think of the function as rotating instantaneously from a slope 0 to slope 1. In which case, if I think of the derivative, it's going to be something like this. Right at 0, it went all the way from 0 to 1. So if I ask you specifically what is the derivative at 0, any value between 0 and 1 is appropriate because you could have captured the function at any point in its turn. Typically, we're going to use the extreme value 1 because we're performing gradient descent. But this is just to give you an idea, right? There's the other kind of activation, which is the max, which we will often encounter. And that is where there are a whole bunch of inputs, say max of z1, z2, and so on, zn. So in this case, let's just say that the maximum value is zn. So this is zn. Then in that case, will perturbing z1 change y? Yes or no?
Small perturbation.
The maximum value is zn, that's the output. So will perturbing z1 change y? It's not the maximum value. If I'm looking at really small perturbations, right, eventually I can find a small enough perturbation that it doesn't cross the end. So does that make sense? If you're not currently the maximum value, then changing that value is not going to change the output. So what is the derivative of y with respect to z1?
0.
What is the derivative of y with respect to zn? So it's going to be 1 for just the maximum term and 0 for everything else, right? And so that's what you will get. And so here's a little proof. Now this is actually another special case of a subgradient, but yeah. Have a timer. 45. 12:30. Okay, that was easy. I think most of you are done. So can you give me the answer to this one? Anybody? So Maria, is the first statement true? What about the second one? What about the third? Fourth? Fifth? Sixth? Because z3 is the largest value, right? So the derivative with respect to z1 and z2 is going to be 0, and the derivative with respect to z3 is going to be 1. Questions? No. Okay, and so here's the backward pass. In the backward pass, if you have activation functions which are not differentiable at some point, so long as the function is continuous, you can always compute a subderivative of sorts, and you can use that in the place of the derivative. So the overall approach for training is as follows. In the forward pass, you're going to pass the instance forward through the net, store all the intermediate outputs. In the backward pass, we're going to sweep backward and iteratively compute all derivatives with respect to weights. The actual loss is the sum of or the average of divergences over all the training instances. So the gradient over here is also the average of divergences over all the training instances. Backpropagation, the rules that we just saw, tell you how to compute the divergence for a single training instance. You'd have to accumulate these over all of your training instances, compute the average, and that's what you would use in your network update. So training by backprop, during the forward pass, you'd be computing all the intermediate values for your entire training set and the loss. During the backward pass, you'd be computing all of the derivatives, computing that average, and using that in your gradient descent rule. So, questions? Yeah.
You're averaging the gradients, then won't you be susceptible to, like, if you have one mislabeled point, then it might like change it a lot because the gradient.
When you're averaging, it doesn't matter whether you're summing or averaging. That effect, that influence remains the same, right?
Yeah, but regardless, when like if you have a mislabeled point, then the gradient would be like super big, so it would like change a lot.
These things will affect it, yes, indeed, right? But that's what you have. You're correct. So now here's the thing. I've just sort of explained the whole thing variable by variable, but you never really perform the computation in this manner. The way we do it for layered networks, it's generally simpler to think of the process in terms of vector operations because the arithmetic is simpler and fast matrix libraries make operations much faster. We can restate the entire process in vector terms, and this is what we will use in any real system. So let's look at one layer of the network. I have a picture on the slides, but let me draw this anyway. If I've got one layer of the network, I have, say, y1 through yn in the previous layer, and maybe z1 through zm in the next layer. Then for any particular zi, I'm going to the actual, for any particular neuron, the zi value is computed as a weighted sum of or the outputs of the previous layer. So I can write this as zi equals summation j wji yj. So the weight from the jth input to the ith neuron is just written like so, right? So now here's what I can do. I can put all of the y's in a vector, correct? And then I can write zi like so. If I want the equation, something multiplies this vector of y's to give me zi, and what is that?
Weight vector.
What kind of weight vector?
Row vector.
It's going to be a row vector, right? It's going to be w1i, w2i, wnI. So I can just write it in this manner, right? Now suppose I wrote this for all of the z's, z1 through zm. Then this is just a collection of z values. Corresponding to every z is a row, which is going to be the row of weights for that z, right? So this would be w11, w21, wn1, because it's the weight from the nth input to the ith output, right? This is going to be w21, w22, sorry, no, is it? No, it's 1, 2, 2, 2, n2, and so on. So I can write the whole thing as a weight matrix where the ith row of the weight matrix represents the set of weights to the ith neuron. Does that make sense to everybody? I see some questions on faces. Does that make sense? So also I can write the biases for all of the neurons as a vector in this manner. So once I write it this way, I can just say plus b1 through bm, right? If I have, does this make sense? So if I write this entire thing as a vector z, and this has a weight matrix w, this is a vector y, and this is a vector b, I can just write z equals wy plus b. That makes sense? And of course, now I can apply activations to these z's to get the y's. And so we've done the whole thing in matrix form. Questions? Yeah. Yes, the y is the output of the previous layer, right? So this is what we will actually use. And once I write things in this manner, then it's very easy to compute the forward pass. All of those crazy loops that we wrote, they don't have to be figured out at all. I can just set y0 as the input x. y1 is simply, z1 is simply w1y plus b1, where w1 is the matrix of weights to the first layer. Now I have sort of switched to using layer indices as subscripts because it's more convenient. But then z1 is just w1y, y0 plus b1. And then y1 is simply f1 of z1, right? And then z2 is just w2 times y1 plus b2. And then y2 is just f2 of z2. And so this is easy, right? I can go all the way to the end. I can get the final z and the final y. Trivial. And so when I write the forward pass in this manner, this is so much cleaner. I can just write y0 equals x, and then each z is simply w times y. Each layer z is simply the weight matrix for that layer times the output vector for the previous layer plus the bias. And the activation for each layer is simply the activation function of that layer applied to z. So if I write the pseudocode, it's very clean, much simpler. The challenge, of course, is that, what does this mean? You have to begin thinking about calculus in terms of matrices and vectors. How many of you are really comfortable with that? Some of you, right? But the rest of you guys, you're probably wondering what's going on. It's very easy. There's nothing particularly complicated. So before I present the backward pass, I'm going to give you some ideas of vector calculus. And for vector calculus, we go back and remember something. It's very simple. The rules for vector calculus are exactly the same as those for scalar calculus, in the sense that if I have y equals f of z, then delta y equals the derivative of y with respect to z times delta z. This is the same rule that we used for scalars. And which is why when delta z, okay, so this tells us two things. First, so if y is a scalar and z is a vector, what is this derivative going to be? Using this rule. So delta z is going to look like so, right? Delta z1, delta zn. This is delta z. If y is a scalar, then delta y is going to be a row vector times this delta z. If y is a vector, what is this intermediate term going to be? Is it square? It's going to be a matrix. It's going to be an m cross n matrix. But then what is the specialty of this matrix? You don't need to think of y as a vector. You can think of y as a vertical arrangement of scalars, correct? And in that case, what is the corresponding row of this weight matrix going to be, It's going to be just the derivative of this yi with respect to z. Right, and the derivative of any scalar with respect to z is going to be a row vector. And so each row over here is going to be the derivative of the corresponding y with respect to z. Does that make sense? And that's just a vector of partial derivatives of the yi with respect to all of the zi's. This is the Jacobian of y with respect to z. So again, once again, you see that the simple rules that we saw earlier still apply, right? But then I can also draw the influence diagrams just as before. Once I figure this out, I can say z influences y, And the edge from z to y carries the derivative of y with respect to z. And so once again, this means that delta y is going to be this derivative times delta z. Right? Nothing changed. This is the same picture as before. And so this is just defining the Jacobian as we just saw. Now the Jacobian, in the case of scalar activations of this kind, I can think of this, the activation function which applies to the vector of z's to give you the vector of y's as a vector function itself, except that each y is now influenced just by the corresponding z. So in this case, the Jacobian is going to be a diagonal matrix. Whereas if you have something more complex like a softmax, the Jacobian is going to be a full matrix, right? But other than that, everything else is the same, stays the same. Now this, so now I can go on and talk about special cases. Where did I keep my chalk here? Standard question. So if I say z equals wy plus b, right? Now we wanted to see the way we defined derivatives. Delta z is something times delta y. If I perturb y by a little bit, that's going to result in a perturbation in delta z. What is the term that must multiply delta y? Over here. It's going to be the weight matrix. It's very easy to see, right? Because I can see this easily enough. Z plus delta z equals w times y plus delta y plus b. So the derivative of z with respect to y is simply going to be the weight matrix w. Right? What is the what is the derivative of z with respect to b? So I say delta z equals something times delta b. If I perturb b a little bit, z changes. Right? So what is this term that multiplies delta b? It's just an identity matrix because every perturbation of b results in an identical perturbation of z. So the derivative of z with respect to b is an identity matrix. Everybody with me? Right. Okay. Now we can go ahead and also have the chain rule as before, and here please keep track of the order in which we multiply things. I can say x influences z influences y. These all are vectors. So what would these edges carry over here? This is going to be the derivative of y with respect to z. This edge is going to be the derivative of z with respect to x. Everybody with me? Right? And I can write delta y equals times delta z. Right? And on this side, I can write delta z equals the derivative of z with respect to x times delta x. So connecting the two up, what would I get? Anyone? I'm going to get delta y equals the derivative of y with respect to z times the derivative of z with respect to x times delta x. Everybody clear? Can I change the order of multiplication over here? Can I change the order? That will not give me the rule that I just wanted, right? Because delta y is a function of delta z is a function of delta x. So that is the order in which it must be multiplied. So as I go from here backwards, the derivatives extend outwards. So every time I take a step back, the corresponding derivative gets multiplied to the right or left? Right, okay? So this is just the simple chain rule for vectors. Now I have the extended chain rule, right? I can just extend this and say, you guys help me. Now I'm not going to solve, I'm not going to say anything We will wait a few minutes till everybody gives me an answer. Someone gives me an answer. Suppose I have something of this kind, where x influences z1, influences y1, influences z2, influences y2, influences some scalar d, right? So then what would these edges carry? Anybody? What does this edge carry?
Derivative of divergence with respect to y.
This is derivative of divergence with respect to y2. What about this one?
Y2 with respect to z2.
y2 with z2. This is z2 with y1. This is y1 with z1. This is z1 with respect to x, okay? So now, what is the derivative of the divergence with respect to z2?
Multiply.
What would this be?
Derivative of divergence with respect to y2 multiplied by,
Derivative,
or derivative of y2 with respect to z2
So-
multiplied by delta z2.
so the derivative of the divergence with respect to z2, you're going to start from the right end, right? So this is going to be the derivative of the divergence with respect to y2 times the derivative of of y2 with respect to z2. z2. This may make sense to everybody? Yes or no, right? Okay, so now what is the derivative of the divergence with respect to y1? Using the same rule, what is it going to be? Anybody in the back? Someone want to answer this? Isaac? Okay, not clear? Where did I lose you?
A couple of minutes ago, I was like,
So where did I lose you? I have a minute,
it's been a couple of minutes.
couple of minutes. So exactly, I can go back. Tell me.
Oh yeah, I'll watch them together.
Okay, somebody else. Dhanil, can you answer that?
You just need to multiply
So so this I can think of like so, right? So the derivative, to compute the derivative of the divergence with respect to y1, I can just say y1 influences z2, influences the divergence. Just skipping everything in between. Correct? And so the derivative of the divergence with respect to y1 is going to be the derivative of the divergence with respect to z2 times the derivative of z2 with respect to y1. I keep right multiplying. Each time I take a step back, and this is easy for us to see, right? This is going to, if you just, and this term was just already computed. And so the derivative of the divergence with respect to y2 is simply the nabla term over here. But then if I want the derivative of the divergence with respect to z2, that's going to be the derivative of, for y2, times the derivative of y2 with respect to z2, right? And then if I want the derivative with respect to y1, I can look at the simplified diagram here, where y1 influences z2, which influences d. So this is going to be the derivative of d with respect to z2 times the derivative of z2 with respect to y1, right? And then if I want the derivative with respect to z1, I can draw this simplified picture here, where z1 influences y1, which influences d. So that's going to be the derivative of d with respect to y1 times the derivative of y1 with respect to z. At each step, I just have to look at the next variable and how it influences the final divergence. So each time I take a step back, all I'm doing is multiplying the latest derivative on the right by the new term. That makes sense? Right? To you guys? Okay. So one final thing. So we have this just for to summarize, if I have z equals wy plus b, and then z finally influences my divergence, then this means that the derivative of the divergence with respect to y is the derivative of the divergence with respect to z times the derivative of z with respect to y, but that is just the weight matrix, right? So also, the derivative of the divergence with respect to b is going to be the derivative of the divergence with respect to z times the derivative of z with respect to b, which is just the derivative of the divergence with respect to z. There's one final funky term here, which is what is the derivative of the divergence with respect to this weight matrix W? And that ends up being a little wonky. To think about how it's derived, you'd want to unravel the weight matrix to a vector and work your way through it. But in this one case, it turns out that the answer of the derivative of the divergence with respect to the weight matrix is going to be the input y times the derivative of the divergence with respect to z. Now, one of the things you want to do is to ensure that the matrix sizes are right. So here, I'm probably going to go a few minutes over and annoy the next instructor. But let's see. If I have y is an n cross 1 vector, z is, say, an m cross 1 vector, what is the weight matrix? It's going to be m cross n, right? And then this, say, influences the scalar d. What is the shape of the derivative of d with respect to z? If z is m cross 1, 1 cross n, right? So the derivative of d with respect to z is 1 cross m. So what is y times the derivative of d with respect to z? This is n cross 1 times 1 cross m, that is n cross m, which is the transpose of this guy, right? So you can check the sizes. So that's simply the derivative of d with respect to the weight matrix is simply going to be the input to this edge times the derivative of d with respect to the output to the edge. Everybody with me? Right. And so having set all of these up, I can just go ahead and apply this for to my network. So within each layer, this is what we had. Yk minus 1 multiplied wk added to bk to give you zk. So this means that the derivative of the divergence with respect to yk minus 1 was the derivative with respect to z times this weight matrix. And the derivative for the bias was simply the derivative of the divergence with respect to z. And the derivative with respect to the weight was simply this y matrix times the derivative of the divergence with respect to z for any given layer. And so now I can just work my way back, right? There's a poll. We'll skip the poll for now. Please check it out. They're on the slides. Actually, I'll give you a minute after this is done. So here's what I can do. Here's my network again with all the variables in vector format. I can define my divergence. This is my chain of influences in this picture. And so I'm going to be representing using this inverted triangle notation to represent derivatives everywhere. So here are all the derivatives for every single edge. But then the thing to note is the derivative of each y with respect to z. These are all Jacobians, because the derivative of the activation output of the activation function with respect to the input of the activation function. So, and the derivative of each z with respect to the previous y, that's just the weight matrices, right? And so this is what the actual influence picture looks like. And then when I work my way backwards, I can keep right multiplying derivatives, right? I have the derivative of the divergence with respect to this y, right multiplied by this Jacobian. And then, at this point, I have the derivative with respect to z. And now I can take a step back and right multiplied by the weight matrix to compute the derivative with respect to the previous y. And then using the other crazy rule that we just saw, I need to compute the derivative for the weights. And the derivative for the weight is simply going to be this y times the derivative for the z, as we just saw. So that can just be plugged in. The derivative for the weight is y times the derivative for z. The derivative for bias is just the derivative for z, right? And then I can just keep working my way back all the way to the beginning using these very simple rules. And so here is the overall backward pass rule for computing derivatives for going backwards through the network in vector form. It's very simple. I have this in pseudocode. I have a couple of slides. Here's how you'd set up for binary classification. Is just binary labels. You do a forward pass and a backward pass. For multi-class classification, these are multi-class labels, and we're going to use the arithmetic we just saw to perform backpropagation. Stop here. Thank you all very much. Sorry for going over a couple of minutes. The story, neural networks are trained to minimize the average divergence over training instances. It's performed using gradient descent, and gradients are computed using backpropagation, right? Thank you.